אוקיי, אז אני שמתי את ההקלטה. יש שאלות? אין שאלות. אז דיברנו על פונקטורים. אז אני רוצה עוד דוגמה נחמד, על פונקטורים וספציפית על שקילויות קטגוריות. אז אני רוצה עוד דוגמה נחמדה על כמה קטגוריות שקולות, או כמה דרכים שונות לתאר את אותה קטגוריה. אם יש לנו חבורה G, יש לנו את הקטגוריה BG. אז זוכרים את הקטגוריה BG? כן? לא. אוקיי, הראה שאתם עושים פרצוף שלו. אז קטגוריה עם אובייקט אחד, ולכל איבר ב-G מורפיזם. בהרכבה זה פשוט כפל ב-G. אוקיי, ועכשיו יש לי קטגוריה אחרת. קטגוריה של G Principal Spaces, זאת אומרת, או Sets. יש לנו קבוצה X ופעולה של G על X, שאני דורש מהפעולה הזאת שתי דברים. להיות חופשית ולהיות טרנזיטיבית. זאת אומרת, אין מייצבים, וטרנזיטיבית מכל נקודה אפשר להגיע לכל נקודה. במבט ראשון זה נראה קצת טיפשי, כי הקטגוריה הזאת, לכאורה יש רק G Principal Space סט אחד, כן? G פועלת על עצמה, בכפל משמאל בוא נאמר, זה G Principal Space, ונראה שהם כולם אותו דבר. אבל הם כולם אותו דבר רק אחרי שבחרנו נקודה. לפני זה הם כולם אותו דבר, אבל לא קנונית. אז עכשיו אני טוען ששתי הקטגוריות האלה שקולות. עדיין כולם מדברים עברית? עושה רושם שכן. Everybody still speak Hebrew, yes? אוקיי. אז בואו נראה. אז הפונקטור לכיוון הזה כנראה הכי פשוט. אנחנו לוקחים, יש כאן רק אובייקט אחד, נקודה, אנחנו פשוט מעבירים אותה ל-G Principal Space הפחות או יותר יחיד. היחיד עד כדי איזומורפיזם, זאת אומרת G פועל על עצמו בכפל משמאל. וכל איבר ב-G מפה נותן לנו אוטומורפיזם של ה-G Principal Space הזה, על ידי כפל מימין. כן, כאן צריך קצת להיזהר, שאם G פועל על עצמו על ידי כפל משמאל, אז כפל משמאל באיבר ב-G זה לא העתקה של G קבוצות, כי זה לא מתחלף עם הפעולה של G, אלא אם כן G קומוטטיבית. אבל כפל מימין באיבר ב-G כן מתחלף עם הפעולה של G.
רמי, לא הבנתי, אתה רשמת פה איזומורפיזם של קטגוריות? כאילו,
שקילות קטגוריות, כן.
מה הקטגוריה מימין?
BG או G Principal Spaces? G Spaces. אני חוזר, G Principal Space זה G קבוצה שהפעולה עליה חופשית וטרנזיטיבית.
נכון, זה אנחנו מכירים, אבל איפה זה קטגוריה? איך זה קטגוריה?
זה קטגוריה, זה קצת קטגוריה מלאה של קטגוריות G קבוצות. G
כאילו
קבוצות
X
זה
כאן
קטגוריה,
קבוע?
העתקה בין G קבוצות זה העתקה שמתחלפת עם הפעולה של G, כן.
אז X כאן הוא לא קבוע, כן.
כן, X הוא לא קבוע, כן.
אוקיי.
אוקיי, אפשר לכתוב ככה.
סבבה.
אוקיי, אז דרך אחרת לראות את השקילות הזאת זה להגיד שיש לנו, אם אנחנו מסתכלים על הקטגוריה הזאת, אז יש בה רק מחלקת איזומורפיזם אחת. וברגע שיש לנו קטגוריה מחלקת איזומורפיזם אחת, אז היא בעצם B, אז אם אני מסתכל על ה... אוקיי, זה תרגיל אולי כללי. Exercise. See if C is a category with one ISO class, אז C שקולה לקטגוריה B and x, כש-x שייך ל-c. אז למה אני מתכוון? אם יש לי אובייקט בכל קטגוריה, אני יכול להסתכל על אוסף כל האנדומורפיזם שלו, אני יכול להרכיב אותם. זה אסוציאטיבי, ויש יחידה, אז מדובר במונואיד. אז בכל מונואיד אני יכול להסתכל על BG, או B גמא. אם יש לי מונואיד M, אז יש לי BM. שזה אותה הגדרה כמו BG למקרה של חבורה, אבל למונואיד. והטענה יש שתי הקטגוריות האלה הן שקולות, והבנייה מאוד פשוטה. יש לנו פונקטור מכאן לכאן, שהוא מאוד פשוט, והוא full faithful ו-essentially subjective, לכן שקולות.
מה זה מחלקת איזומורפיזם? זה של אובייקטים או של
של אובייקטים, מחלקת איזומורפיזם של אובייקטים, כן. זאת אומרת שכל
כאילו...
האובייקטים איזומורפיים, אני צריך שכל האובייקטים יהיו איזומורפיים. ברגע שכל האובייקטים איזומורפיים, אז כל קטגוריה הופכת ל-BG או BM.
איך זה הגיוני כשיש לך למשל חצי חבורה למחצה, אז כאילו, זה לא איזומורפי לחבורה, זה כאילו...
לא, זה לא, אבל גם זה לא חבורה.
אוקיי.
NDX זה לא חבורה, זה מונואיד.
סבבה.
עכשיו, כן, אז בהקשר הזה יש עוד הערה שיותר מתאימה לפרק הבא, אבל כבר אפשר להגיד אותה עכשיו. אז יש מושג של גרופואיד. גרופואיד זה קטגוריה שכל המורפיזמים בה הם איזומורפיזמים. וזה בעצם אומר שמנקודת מבט של תורת הקטגוריות, הגרופואידים הם לא מאוד מעניינים. כי יש לנו מחלקות איזומורפיזם, אולי יש מספר מחלקות איזומורפיזמים, אבל להבדיל מקטגוריה כללית שבה בין אובייקטים לא איזומורפיים עדיין יכול להיות מורפיזם, פה בין אובייקטים לא איזומורפיים לא יכולים להיות מורפיזמים, כי כל המורפיזמים הם איזומורפיזמים. זה אומר שבעצם כל מחלקת איזומורפיזם היא חיה בעולם שלה, נפרד לגמרי, והן לא מתקשרות אחת עם השנייה. ולכן, זה נאמר BG1 וזה BG2 וכו'. זאת אומרת, אם יש לנו גרופואיד, אז הוא נראה כמו מין איחוד זר כזה של BG'ים, שכל אחד מהם חי בפני עצמו. ולכן במבט ראשון נראה שלתורת הקטגוריות כאן אין שום יתרון על תורת החבורות, זאת אומרת, אין שום הבדל בין לחקור גרופואידים ובין לחקור חברות. שזה במובן מסוים נכון, אבל אוקיי, נדבר על זה אחר כך ונראה שיש איזה שהם הבדלים בכל זאת. אוקיי, אז עכשיו בואו נחזור רגע לדוגמה של... אז יש לנו BG, ועכשיו יש לנו שתי דרכים שונות לאפיין את BG. אחת זה נקודה, לתאר את BG. אחת זה נקודה ו-G אוטומורפיזם, ושנייה זה G principal spaces. עכשיו אני טוען שבמקרים רבים יש גם דרך שלישית. אז למשל, אם B שווה ל-SN, אז BG שקול ל-set of odd n. אבל לא כל הקטגוריה של, לא, כן, התת קטגוריה מלאה של קבוצות בגודל n, אלא רק אני לוקח את כל האובייקטים, קבוצות בגודל n, ומורפיזם אני מרשה רק איזומורפיזם. אז אני אכתוב את זה ככה, הגרופואיד המתאים להם. יש לנו קטגוריה, אנחנו יכולים לזרוק לפח את כל המורפיזם שהם לא איזומורפיזם, ולקבל גרופואיד. מכל קטגוריה אפשר לעשות גרופואיד. אז אני אומר שאם G זה Sn, אז קל לראות שהגרופואיד המתאים יהיה פשוט קבוצות בגודל n. סליחה, שהקטגוריה BG תהיה הגרופואיד של הקבוצות בגודל n. לא הקטגוריה של הקבוצות בגודל n, אלא הגרופואיד של הקבוצות בגודל n. למה? בגלל אותה למה, בגלל אותו תרגיל. יש לנו, תופסים קבוצה אחת בגודל n, הרי כולם איזומורפיות, כולם ביאקטיביות, ומחשבים את חבורת האנדומורפיזם שלה. אבל מכיוון שאנחנו הרשנו רק הפיכים, אז זה בדיוק אוטומורפיזם שלה, שזה בדיוק Sn. באותו אופן, GLN זה הגרופואיד המתאים vect of, אני כתבתי order כאן, זה לא order, זה size. וכאן זה off dimension n. ברור למה זה נכון? אותו הסבר בדיוק. עכשיו B-O-N, אבל כאן חשוב לי שאני עובד מעל שדה סגור אלגברית. אחרת יש גם גרסה של זה, אבל זה יותר מסובך. אז הגרופואית של מרחבים ריבועיים, quadratic vector spaces, מרחב ליניארי ביחד עם תבנית ריבועית, לא מנוונת. מ עד n. שוב, מעל שדה סגור אלגברית הם כולם איזומורפיים, וחבורת אוטומורפיזם בסיסי.
השוויון כאן זה איזומורפיזם,
זה איזומורפיזם
נכון?
כמובן. שקילות, זה שקילות.
שקילות.
שקילות קטגוריות, כן. זה קטגוריות לא איזומורפיות כי הן בגדלים שונים, אבל אמרנו שאיזומורפיזם של קטגוריות זה לא דבר שנעבוד איתו בדרך כלל. אז בכל אחד מהמקרים האלה, בואו נסתכל על המקרה הזה, הוא אולי הכי מעניין. אז יש לנו עכשיו 3 קטגוריות שקולות. אחת BG שאנחנו מגדירים בצורה הכי down to earth, נקודה ואוטומורפיזמים. שנייה, G principal spaces, ושלישית, וקט, כן, מרחבים וקטוריים, או מרחבים וקטוריים עם תבנית, או קבוצות סופיות, כל פעם תלוי בהקשר, אז בואו נדבר על המקרה הזה, ואז זה מרחבים וקטוריים. אז כרגע תיארתי, איזה פונקטורים בעצם תיארתי? תיארתי את שני החברים האלה. אז אני רוצה לתאר עכשיו עוד כמה. כן, זה לא ברור שתמיד אפשר לתאר במפורש, כי זה שהקטגוריות שקולות זה נובע בעצם מאקסיומת הבחירה, יש פונקטור שהוא fully faithful ו-essentially subjective. אבל בהרבה מקרים יש גם, למשל את שתי הפונקטורים האלה, גם אפשר לתאר. אז הפונקטור מ-vector spaces ל-G-principal spaces זה די נחמד, למי שיש ניחוש, יש מרחב וקטורי, איך אני בונה ממנו G-principal space?
על ידי הכפל במטריצות, במערכות ליניאריות.
אבל את מה אני מכפיל?
ה-G כאן זה GLN, כאילו...
G זה GLN. כן.
אוקיי.
יש מרחב וקטורי, המרחב וקטורי עצמו הוא לא GLN principal space, הוא בצורה לא נכונה ומגודל לא נכון, כן? הוא n ממדי במקום להיות n בריבוע ממדי, והוא גם מרחב ליניארי ולא חבורה. כאילו, הוא ישר, כן? יש בו... GLN היא לא נראית כמו מרחב ליניארי, היא דומה למרחב ליניארי, אבל קבוצה פתוחה במרחב ליניארי והיא לא מרחב ליניארי. אבל כן, כפל במטריצות זו תשובה נכונה, אבל השאלה היא על מה היא פועלת. היא לא פועלת על V, היא פועלת על מרחב אחר, שגם עדיין שאפשר להכפיל עליו בו.
של האנדומורפיזמים?
קרוב, אבל לא, כי אנדומורפיזם של מרחב אבסטרקט טבעי, אני לא יכול סתם להכפיל במטריצות. כי המטריצות הן מטריצות סטנדרטיות, הן לא העתקות מ-V ל-V. הן יהפכו לעתקות מ-V ל-V אם נבחר בסיס, אבל בפני עצמם הן לא העתקות מ-V ל-V. אבל זה כבר ממש קרוב. גם אנדומורפיזם זה לא יהיה G principal space, אז אתה בטח רוצה לדבר על אוטומורפיזם, כן? כי אז זה באמת ממש מתאים בגודל ל-G, אבל G עדיין לא ממש מתחבר לזה, צריך... דומה ל-G, אבל...
אז של הומומורפיזמים מ-KN ל-V.
בדיוק.
כאילו, אוקיי.
או במילים אחרות בסיסים, ב-V. או בסיסים או מערכות קואורדינטות. עכשיו כאן אני כמובן תמיד מבולבל. מטריצות העתקות מ-KN לעצמו, אז צריך להרכיב אותם עם העתקות מ-KN ל-V, אז ההרכבה מימין כנראה, כי אנחנו קודם מבצעים אותם, ואז זה פחות מתאים. אז צריך או להפוך את הסדר, או לעשות אינברס, אבל זה לא מאוד חשוב, כן? אבל בעיקרון, כן, אוסף כל הבסיסים, או אוסף כל ההומורפיזם מ-KN ל-V, לא ההומורפיזם, כל האיזומורפיזם, כן? אנחנו רוצים שהם יהיו הפיכים. אז זה דרך נחמדה, ממרחב וקטורי לבנות G principal space. הפוך, מ-G principal space, איך אנחנו בונים מרחב וקטורי, n ממדי. נכון, אפשר להגיד כל המרחבי וקטורים n ממדיים זה אותו דבר, בואו ניקח את Rn או Kn, אבל זה לא יעבוד, כי אנחנו רוצים שזה יהיה פונקטוריאלי, אנחנו רוצים איזושהי בנייה טבעית, אמיתית, שנדע מה לעשות מורפיזמים. כן, פה לא אמרתי מה לעשות למורפיזמים, אבל זה די ברור מה לעשות למורפיזמים.
אפשר לקחת את חוג החבורה, או משהו בסגנון?
חוג החבורה מאוד מאוד גדול. יש לנו G-Principal Space, אנחנו רוצים לשחזר ממנו מרחב וקטורי. עכשיו יש לנו רמז, ה-G-Principal Space זה חושב שהוא אוסף כל הבסיסים במרחב הוקטורי. טוב, אולי זה לא רמז מאוד טוב. לא, האמת, לפיזיקאים זה רמז טוב. מה זה וקטור? אוקיי, הרמז האמיתי זה, תחשבו על מה זה וקטור כשפיזיקאים מגדירים אותו. איך פיזיקאים מגדירים וקטור, אתם יודעים? נו, לוקטור לפעמים גם מציירים ציור, אבל ככה, כן, לוקטור לפעמים עושים ככה, אבל כשמדברים על טנזור, אבל אחר כך אפשר לחזור על זה לוקטור. כשמדברים על טנזור בהרבה מקומות, לא, לוקטור גודל וכיוון זה עובד, אבל טנזור כללי, זה לא עובד. טנזור כמו שאמרנו, זה פשוט איבר במכפלה טנזורית של V עם עצמו כך וכך פעמים, ואז גם עם V סטאר כך וכך פעמים. אבל הם אוהבים לעבוד בקואורדינטות, אז הם אומרים וקטור, זה פשוט עניית מספרים, זהו. אבל זה לא בדיוק, כי זה תלוי בבחירת בסיס, טוב, הם קוראים לזה מערכת ייחוס, אבל אותו דבר. אם נבחר בסיס אחר, אז נקבל ענייה אחרת של מספרים. אז הם אומרים, זה עניית מספרים שמשתנה בצורה מסוימת שמחליפים בסיס. אבל בואו נגיד את זה קצת אחרת, זה בחירה של עניית מספרים לכל בסיס, כך שכשאנחנו עוברים מבסיס לבסיס, הענייה משתנה בצורה מסוימת. אז אם כבר יש לנו G-Principal Space, שאנחנו בדיעבד יודעים שהוא יהיה אוסף כל הבסיסים, אבל כרגע הוא סתם G-Principal Space. בואו נחשוב עליו כעל אוסף כל הבסיסים, ואז מה זה וקטור? זה לכל איבר ב-G-Principal Space הזה, עניית מספרים, זאת אומרת איבר ב-KN. זאת אומרת, אני יכול להגדיר ככה, בהינתן let S, B, GLN, בין space, אז בואו נגדיר V של S, זה אוסף כל הפונקציות מ-S ל-KN, זה מרחב עצום. אבל עכשיו נשים תנאי שישפר את המצב. עכשיו, כן, אל תיקחו אותי במילה עד כדי אינברס כאן, אבל בעיקרון אני רוצה ש... F, אני חושב ששל GX שווה... טוב, אני פשוט לא אתחייב על שום צד. G בחזקת פלוס מינוס 1. אני פשוט לא זוכר אם זה 1 או מינוס 1. אפשר כמובן לשבת ולהבין, אבל לא התכוננתי מספיק טוב.
אני די בטוח שזה G מינוס 1, כן. אוקיי, אבל לא משנה.
נשמע טוב.
אוקיי.
נשמע הגיוני, כן. אז ככה אפשר מ-G-Principal Space לייצר מרחב וקטורי אמיתי. אפשר להגיד שזה דבילי, כן, זה מרחב ממדי, זה RN, אבל... אוקיי, אז הנה ניתן דוגמה איפה זה נותן משהו לא דבילי. אנחנו ניקח...
מה זה G בהגדרה הזאת?
G קטן?
כן.
G קטן זה איבר ב-GLN. GLN ו-S קטן זה איבר ב-S גדול. G קטן פועל GLN. אז אתם רואים שאם S זה אוסף כל הבסיסים, אנחנו באופן טבעי משחזרים את G עצמו, את V עצמו. כמובן לא מרחב ששווה ל-V עצמו, כי אין דבר כזה ששווה, אבל איזומורפית, טבעית, ויש שם בעצם איזומורפיזם של פונקטורים, והפונקטורים האלה הם הפוכים אחד לשני. סבבה?
רק תרשום X במקום S.
כן, סליחה. עכשיו סבבה. אז גרסה קצת פחות טריוויאלית של הדוגמה הזאת, זה וקטור בנדלים, כן? יש לנו וקט M, וקטור בנדלים מעל יריעה M. נו, אוקיי, בואו נניח מעל המשים. אז וקטור בנדלים מעל יריעה M, אז הגדרנו מה זה. עכשיו אני טוען שהקטגוריה הזאת שהיא שקולה ל-G טורסורס מעל M. מה זה G טורסורס? זה די דומה ל-G פרינסיפל ספייס, אבל עכשיו אני מוותר על הטרנזיטיביות. זה מרחב עם פעולה חופשית, אבל אני רוצה שתהיה לו העתקה ל-M, שכל CV יהיה מסלול. אז G טורסור זה X מועתק ל-M, סליחה, ל-M, G פועל X, בצורה שההעתקה הזאת היא אינווריאנטית, ופי אינברס של A is G transitive. וגם אני רוצה ש-G free action. Okay, so I will pass to English now.
Can you repeat the transitive?
Transitive, yes. So the fiber of any point for any A in A, M, sorry, I want that the fiber of any point will be G transitive and the action will be free. So the fiber of any point is G principal space. So it's like bundle but of G principal spaces. So just a previous, what?
What does it mean, just G transitive?
Transitive, the action of G is transitive, meaning any point can be transferred to any point.
Okay.
So basically, a torsor is family of G principal spaces. So maybe they are not really. So the notations here are maybe not very standard. So I think in some places torsor and G principal spaces are just synonyms. But I think it's more common to have this difference. So G principal space is the same like torsor over a point. So it's just a space with a transitive free and transitive action. And torsor is a family of such. I think it is the standard terminology. I might be wrong. So in one of my old papers, I didn't know it, and I thought that torsor have to be transitive, and family of torsors are just families. And what is actually torsors is called family of torsors. So this better terminology is DSR, but I think the more standard terminology is that principal spaces are just one space, and torsor is family of G principal spaces. So the same argument as before shows that vector spaces, that vector bundles over a manifold. So this category is equivalent. Here I have to be careful, sorry. Yes, this category is equivalent to category of G torsors. But I have to be careful, also before I had to be careful. So it's not the category of vector bundle itself, but the groupoid of vector bundles. So I consider all vector bundles. And okay, if I should be more careful, GLN, and here is vector bundles of dimension n. Yeah, so also before I wrote here vect, but it's of course vector space of dimension n, and I have to consider the groupoid of such. So to throw away all the isomorphisms, all the morphisms which are not isomorphisms.
Do you have to do so? Because equivalence of category.
If I want the category to be equivalent, then yes, because the category of torsor is a groupoid. And moreover, it's a groupoid with unique isomorphism class. It's only n-dimensional.
No, I mean, I meant before because you said
So the
the
same principal
equivalence.
spaces. The
The,
equivalence of categories. So
yes.
BG, G principal spaces, and if G is GLN, vector spaces of dimension n.
When you add groupoid,
Groupoid of vector spaces of dimension n.
you mean you mod by the isomorphism classes?
No, I don't mod. I throw away all the morphisms which are not isomorphism.
Oh, not invertible in the vector space. Okay.
Yes.
Okay.
Okay. So we have groupoid. Okay, so this is a nice point of view. It's somehow, I don't think it's better than the standard point of view on vector bundles, but it's complemented. So you often want to use one and often the other. For example, if you want to use vector bundles with quadratic form, like Riemannian vector bundles, then instead of using BG, you can do BGLN, you can do, instead of using GLN torso, you can do ON torso. If you want to consider symplectic vector bundles, you can do SPN torso.
Can you
But
please explain again how is the right-hand side dependent on M?
right-hand side, you mean
The
M
GLN
like this?
torso.
GLN torso over M, like this. You see, there is a map to M, and the fibers have to be transitive and, in fact, principal. Yeah, so another definition of, if you want to consider like abstract torso, not above anything, then you basically can say, consider just a space with a free action. It's not always accurate, but let's start with this. And then you can quotient by this free action, and then this torso will be torso over the quotient. Now one has to be careful, because if you have a free action, it doesn't necessarily mean that the quotient will be nice. And if it's not nice, you still can consider it as a torso over something which is not nice. So it depends on taste. A very nice example is the action of the multiplicative group, the group GM. So you pick a field and then you take all the elements which are not zero, but let's take R, so just the group R star, acting on the plane without zero, but not acting as usual, like with homotopic. This would be also a very nice example. It will give you torso over the projective line, but acting like this. When you multiply one axis by lambda and another divide by lambda. And then you can see what will be the quotient, and you see that there's no real quotient. The quotient is going to be not Hausdorff, because you have the two axes, and they're kind of not Hausdorff. So I don't know whether we want to call it a torso or not, but even if yes, it's torso over something which is not Hausdorff.
May you please explain again why is it isomorphic to the groupoid of vector bundles over M?
So I didn't actually explain. I just said that it will be as before. So if M is 1 point, then here you have just vector spaces, vector bundles over point is vector spaces, and here you have GLN principal spaces, which is BGLN. And this I explained before. So now we can repeat the same construction and get equivalence like this. So it's an exercise, but it's not hard. Okay, so now if you play with a group GLN, you can get some funny things. So first of all, you can get bundles with scalar product. Then you can get bundles with symplectic form. But there are other groups in the world. I don't know if you know algebraic groups. There is E8 and G2. So G2. So you can ask, what is E8 torso? What is G2 torsos? And you can think about them as vector bundles with some additional structure. What is the structure? Structure of a G2 torso. So it allows you to ask questions that you didn't ask before. So you can take some theories that you did for vector bundles and take them for general G torso and get some nice new things. So here, in order to be fair, I need to say something. That in fact, if you want to see this construction even for ON, so if you want, starting with ON torso or ON principal space, to build a vector space with a bilinear form, what you implicitly do here, you use a representation of ON, the standard representation of ON. ON acts on vector space. Even in GLN, you see it. So, oops, sorry. We talked here about isomorphisms between Kn and V. So we use the fact that the group GLN equipped with n-dimensional representations that we call standard. So if we actually want to do this construction, then we need to have this representation. And the group G2 or E8 not really have one representation that you call standard. But you don't have to think about it as a disadvantage. You can think about it as advantage. So you can start with any group G and any representation V. And then you have the category of torsos, of G torsos, say, over M. And this representation actually gives you a functor to bundles. Yeah, actually for vector, but maybe it's better to write bundles for vector bundles. Bundles over M. Any representation gives you such a functor. And if your group G is GLN and this is a standard representation, or in fact any representation which is isomorphism, so you have to representation is a map between G and GLV. So if this is an isomorphism, then this functor going to be an equivalence of categories. But in general, it does not necessarily. Even in general, it's not an equivalence of categories. If G is ON, so this functor going to be the forgetful functor. So this we can think of as vector spaces with a quadratic form, and we get a vector bundle, sorry, with a quadratic form, and applying the forgetful functor, we just get vector bundles. So if we have some representation of some weird group, I don't know, G2 or E8 or any other group that you like, so torso over this group, you can think about them as vector bundles of the corresponding dimensions of the dimension of your representation with some additional structure. And this structure you can think of, and this functor you can think of just as a forgetful functor. You forget the additional structure. Yeah, so vector bundles are just GLN bundles, and other bundles are and you can consider, so G torsos often are called G bundles because they're like versions of the notion vector bundles. Yeah. Or another way to think of it is if you have a morphism between two groups G and H, then you have a functor between tau G and tau H. And if if H is GLN, so the second thing is just vector spaces, so you get functor from torsos to vector bundles. Okay, so another, you can get here interesting examples even if you talk about GLN, because GLN have, oops, sorry, GLN have more than just one representation. Yeah, GLN have, for example, the representation, the joint representation, GLN acts on matrices. n by n. And now you can apply this construction, and you start with GLN torso, which is, as you know, just a vector bundle, and get a new vector bundle. So you get a now just for a moment forget about M, just let's assume M is a point. So you can get a functor from vector spaces to vector spaces. So each time you have a representation of GLN, you can get a functor from vector spaces to vector spaces. And this and what will be this functor in this case if you start with a joint representation of GLN? Anybody have some guesses? Is the question clear? The question itself clear or not?
Is the question to construct a functor from the category of vector spaces to itself?
But not just a functor. So we already described some functors. So now I want more explicit description. So I said that if we have any representation of GLN, then we get automatically a functor from vector spaces to vector spaces. Why? Because we said before that we get a functor between GLN torsos to vector spaces. Or maybe even I will say it differently. I take GLN. If I have a representation of GLN, it basically means I have a map between GLN and GLM. So this is a category, and this gives me a functor between GLN principal spaces and GLM principal spaces, or equivalently between BGLN and BGLM. So this is a functor, this is a category of n-dimensional vector spaces, and this is a category of m-dimensional vector spaces. So I get a functor between the category of n-dimensional vector spaces to m-dimensional vector spaces. Any representation of GLN gives me such a functor. So if I have this representation, a joint representation, so the action of GLN by conjugation on n by n matrices, what will I get?
How is GLN defined? The
GLN is just invertible n by n matrices.
Is it something like moving a basis to a basis?
It depends. I need more
You
details.
don't know how it acts. Can you say again how it acts? What do you mean
So
by
how
acting?
GLN acts on matrices? Just by G, A, G inverse. And G acts on A basis. So this gives me a map between GLN to, in fact, GLN square. And I ask, what functor does it give me from vector spaces, n-dimensional vector spaces, to a square dimensional vector spaces? Okay, I will say the answer and consider it as an exercise. So I claim that this is this functor. Take any vector space to the vector space of its endomorphisms. And in fact, you can describe not only this functor, but many. So in a sense, okay, under some condition, any functor can be described as by this one representation of GLN, and any functor from the groupoid of n-dimensional vector spaces to the groupoid of m-dimensional vector spaces can be described by one m-dimensional representation of GLN. So all the sure functors that we discussed before can be described by one, each of them by one representation. And the functor of taking tensor product of V with several copies of itself also can be described by such. I have a problem here. Yes, this is a functor, but one has to be very careful here, because morphism between two spaces is contravariant on the first one and covariant on the second one. So on the first glance, this does not look at a functor at all. It's not contravariant and not covariant. But since we are working for the groupoid of all vector spaces and not the category of all vector spaces, we actually can make a functor out of it. So if we have a vector space, and if we have morphism, invertible morphism between two vector spaces, it gives us invertible morphism between the corresponding spaces of endomorphisms. One has to think about it a little bit, but it can be done. And in general, if you now consider the functor V maps to V tensor V many times and then tensor V star with itself many times, and then you get, so again, this is not an actual functor, but if you start with a groupoid of vector spaces, it is a functor. It corresponds to a very explicit representation. Just substitute Kn to this functor, yes, and then you get a representation of GLN. And one can say that the notion of tensor is just tensors over V, like tensors of this type over V, is just substitution of V into this functor. And now you can recall that we have had here this alternative way to, or a way to describe all those functors. So how starting with the G principal space we get a vector space, or how, and we said that the vector space will be the vector space of all functions from the G principal space. Yeah, well, we had it here. The change in some way. So the exercise, just think about it, substitute all these for tensors, for this functor that I described below, and you will get this alternative, this physics definition of tensors, instead of defining the abstract tensor product, defining the notion of tensor, or something that give you a huge table of numbers for any choice of basis, in a way that when you change the basis, change in it according to some formulas. Yeah, so when I first read or heard about this definition of physics as for tensor, I thought, okay, it's too much low tech, yes, not too much hands-on without using this a bit more sophisticated language of tensor products. They're making their life much difficult because of lots of formulas. But then after I revisited this with these descriptions, and okay, now it's look the opposite side, very high tech, all this category theory and G-torsors, and at the end it's just the same thing. Okay, I think it's a good time for a break. What?
Okay, just what do you mean by substitute? You say substitute the Kn to what do you mean?
To this functor. So I said that any functor, I said that any representation of GLN or any map between GLN to GLM give you a functor between n-dimensional vector spaces to m-dimensional vector spaces. But to be more accurate, between the groupoid of n-dimensional vector spaces to the groupoid of m-dimensional vector spaces. So it's also true the other way around. If you have functor between the groupoid of n-dimensional vector spaces to the groupoid of m-dimensional vector spaces, it comes from a representation. And how do you find this representation? You just substitute into this functor the space Kn. So you can do it with this functor. When you substitute in this functor the space Kn, you get like this space when V is Kn. So you know how this space looks like when V have explicit basis. Then this thing also have explicit basis, and then it's just huge table of elements, yes? But now it's not just a vector space, it's also a representation of GLN, because each time you have a like transformation between V to itself, so change of basis, you know how this change of basis acts on these huge tuples of numbers, tensors, yes? And now, if you want to define a tensor in an abstract space V, which is not necessarily Kn, what you actually get, okay, you can say just take this product and this is, and elements in this product will be V. But if you don't know what is tensor product, but you do know all these long stories that I just told you, you can say, okay, what is a tensor in V of this type? It's a huge tuple of numbers, or table of numbers, for each choice of basis in V. So for each isomorphism between Kn and V, you have element here in Kn times Kn times Kn star. So elements here is something very explicit, it's just many, many numbers. So for each basis in V, you have element here, and now you want it to change according to certain rule because you have a representation of GLN there. Okay? I hope they did not confuse you too much. So let's meet in 7 minutes. So 5M17.
Rami,
Yes.
could you please say the topics for the next lecture before lecture, so we can go over it a little bit
So next, you mean the current or the one that will be next week?
next week?
Yeah, so I more or less want to follow the thing that's on the website. I'm doing it rather slowly. So today we're still on chapter 3, on the third lecture. I hope to finish it today and start and, okay, I can say hope to finish, but this will be too naive. So let's be less naive. Finish this today and start 4. So next week, finish 4, maybe not finish 4, advance in 4, and then maybe it's to start 5. Yeah, I think I want to start 5. I thought maybe I will skip it, but no, I think I want to do 5. So, but I'm not really sure how fast I will go or how slow I will go, because we're going either slowly. So each time I teach it, I go more and more slowly because each time I want to tell more and more things around it, which are kind of, yeah, forward I go slower, but I go to the side. So okay, so meet in 6 minutes now. Okay, sorry. So we can continue. Can we continue? By the way, Guy, how are you here? Guy?
Yes.
Yeah. I didn't ask you what you did last time. Did you
I
do you
want
do any of the examples that are written here now, like Gala correspondence?
Gala correspondence. I think I didn't do it in the end.
Okay, in fact, this is the last example that's left here, so let me do it now. So Galois correspondence also can be sort of equivalence of category. So do you all know Galois theory?
No.
No. Okay. So you have a field K and a field extension L. So you can consider automorphisms of L over K. So it maps between L and L, automorphism of fields that preserves K. So this itself is not a functor, but I think it should not be a functor. But there are many functors that are related to it. Okay, so there is a notion of Galois extension, so extension that satisfies something. Basically, this group is large enough. And the main theorem in Galois theory says that if you now consider a field, I don't know how to call it, M over K, which is a subfield of L, so field in the middle. So you can consider automorphisms of L over M. Yes, this will be a subgroup of automorphisms of L over K. And you can start with a subgroup H in automorphisms of L over K and consider now the field of H invariants in L. So you get maps from two sides. So you can have the collection of all fields like this and collection of all groups like this. So both of those collections are categories, but in fact they're even better. They're just posets with respect to inclusion. So you have two maps like this, and those two maps are order inversing maps. So you can consider both of them as contravariant functors between one category and the opposite category of the other. And they're not only order inversing, they are also inverse one to the other. So those two posets are isomorphic up to inversion, or in other words, those two categories are equivalent, again, up to taking the opposite category. And now you can take one nice example in the case that L is equal to K bar. So any field can be embedded into the algebraic closure. So, but here you have to be careful because this embedding is not unique. So you can consider the Galois group. So this group of automorphisms under some reasonable conditions on L. So when the extension is Galois extension, this group of automorphism is called the Galois group of L over K. And the Galois group of K bar over K is called and denoted like this. It's called the absolute Galois group of K. So
What is K bar?
the algebraic closure of K. Do you know what is algebraic closure?
No.
You know what is an algebraically closed field?
No.
So you know that over R, you have polynomials that does not have roots. For example, x squared plus 1, yes?
Yes.
But you know that this polynomial have a root over C.
Oh, okay, I get it.
In fact,
So-
any polynomial over C have a root, which is not trivial theorem, but it is correct.
Okay, good.
So C is algebraically closed. So algebraically closed field is a field that have all the roots of all polynomials. Algebraic closure, it's so it's not obvious this thing can be done, but it's rather straightforward. You start with a field, and then you add to it all the roots of all polynomials. So in principle, you can think what happens if I have now new roots of new polynomials, so you can repeat this procedure many times, but I think in fact you don't really need to. Yes, you can just do it in one step. But even in doing it in one step, it's hard because there are many So you need to use some transfinite induction, some axiom of choice, but basically this procedure that can be done, but not in a canonical way. So there is only one algebraic closure up to isomorphism, but this isomorphism is not unique. So in a sense, it's kind of misleading to say, let's take the algebraic closure. There are many algebraic closures, and it's a bit misleading. So the absolute Galois group of K is just a Galois group of the algebraic closure of K over K. Or maybe here it's a good place to comment about it. So this notation is a bit misleading because it assumes that we have one algebraic closure and we have more than one. They're all isomorphic, but we have more than one. But in fact, what we can define is not the absolute Galois group, it's the absolute Galois groupoid. So we can define B gal of K. This is very well defined object. It does not depend on any choices because this as a category equivalent. So this is an exercise, an easy one, to the category of all algebraic closures of K. So of K. So the algebraic closure, as I say, is not unique. So algebraic closure of K is a field that contains K, which is algebraically closed, and such that any element in this field is algebraic over K, meaning it's a solution of certain polynomial over K. So we didn't add anything that we don't need to add. So since they're all isomorphic, again, the same proof work. They're all isomorphic, so we can, when we want to describe this category, we can choose one of them and consider its automorphisms, which is exactly the absolute Galois group of K. So
on the right hand side,
BG.
on the right hand side is the groupoid.
It's a groupoid, yes. Fields only have isomorphisms. No,
So-
it's not true. They only have one-to-one maps between them. But I think in this case, any map between any map between the algebraic closure going to be an
Anyone
isomorphism.
respects the base field.
What?
Anyone-
That be yes over K, of course, yes.
Is it okay? Okay, this is isomorphism. Just if it's
This?
morphism.
This is an equivalence
No.
of categories.
I mean, if you have you
So
claim
any map
it-
between fields is one-to-one. This is automatic.
Yes.
And I think in this case it also has to be onto. אל תתפוס אותי על המילה. I should check. I can check after the class, but it's easy to verify it.
That's true.
It's okay.
If now it's over the low field, then it's true because the roots of a polynomial goes to the root of the same polynomial.
And this is now finite dimensional, so there is no problem. Yes.
Exactly.
Okay, thank you.
Okay, exercise. Okay, so we don't actually have the absolute Galois group as a well-defined object, but we do have the absolute Galois groupoid. And subgroups, so now I can consider the subgroups of Gal K. And this is in one-to-one correspondence with subfields of K bar. But subfields of K bar is not the same as abstract fields. Abstract field extension of K, because any abstract field extension of K, like fine dimensional, or no, sorry, algebraic field extension of K, can be embedded to K bar, but not in a unique way. But I can consider all the subgroups, but not up to equality, and not as just as a poset, but actually as a category. When I also allow conjugation. So a map between two subgroups now will be conjugation. Yeah, so here maybe if I want everything to work correctly, I probably need that K will be separable. And if you don't know what is separable, so just take K to be of characteristic 0. And now I claim that I have the this category of so let's define definition sub of G. So the objects will be just subgroups of G, and morphisms will be I think like this. Yes, it will be so more between H1 and H2 will be all the G at such a G H1 G inverse is in H2. And now sub of G is this is objects is equivalent, or the opposite category of sub of G is equivalent to fields over K with the category of field extension. And the content of this theorem is in fact just Galois theorem.
What is the O? What is the 0?
Opposite, sorry. Okay. Okay, so another nice equivalence of categories. This category and the category of G transitive spaces. So the category of subgroup of G is equivalent. No, I'm wrong. Oh, am I? No, I'm right because I allowed conjugation. I'm right. I think so. Just yes, because if I have a subgroup of G, I can map it to G modulo H. And again, this is fully faithful and essentially surjective functor. So here it's important that I'm allowing conjugation. So a subgroup is isomorphic to its conjugation by some element. And this is again, because if you have G transitive space, you cannot actually choose. If you have G transitive space, you cannot actually choose get a subgroup. So in order to get a subgroup for a G transitive space, you have to choose a point and consider the stabilizer. And choosing different points give you different subgroups, but they are all conjugated. So in our category, they will be all isomorphic. So what we got is that Gal K transitive spaces is equivalent to fields over K. Again, we need K to be perfect, which equivalent to the fact that K bar over K is separable, which is guaranteed if K is of characteristic 0. So you can ask what happens when we just take spaces. Gal spaces. So just sets with action of the absolute Gala group. And here the answer will be just, okay, maybe I'm missing here some point because I think it's okay. I think it's okay. Yes. So here's the answer. So what? How far spaces from transitive spaces? Not that far, because we know that any transitive G set is just union of several G sets. Disjoint union. So we basically need to take products of several field extensions, and there is no name for these objects. It's exactly commutative, unital, nilpotent-free algebras over K. So this is the same as algebras over K, but I have to add. So commutative, unital, nil free. So no nilpotents. Oh, it's for in this case it's just called semi-simple. Semi-simple. No, I also no, it's not all the algebras. They have to be. God. I want to say finite, but finite will only correspond to finite spaces. So let's do here finite Gala spaces, and here we'll do finite dimensional. You can have a version for non-finite dimensional, but then you have to describe in another way also algebras. So this is Galois correspondence in the categorical level. On the level of content, so when you try to prove this theorem, it does not have more information than the standard Galois theorem, just equivalent to the standard Galois theorem, but of course, okay, this can be sort of a reformulation, this more categorical language. Okay, so now I want to talk about the topological version. So are you familiar with the notion of coverings? Okay, so covering is a I even discussed this in the notion of covering this course. Yes, so it's a map between two topological spaces, which is locally look like projection with discrete fiber. Yeah, so it's fibration or locally trivial fiber bundle with discrete fiber. And now if I have a covering and say X is pointed and say also Y is pointed, and of course I want the point to lie over the point, I have several interesting things. So I have, what happens here? I have the group pi1 of X with respect to X0. Everybody know what is pi1? And this pi1 naturally acts on the fiber of X0. Inverse of X0. And also I have, okay, let's start with this.
How does
What?
the action defined? How does the action define?
Okay, this is something that comes from homotopy lifting theorem. So basically you start with some point in the fiber and you have some loop downstairs. So you try to lift this loop. So the statement is that you can lift this loop uniquely, but not as a loop, but as a path. So you follow the loop downstairs and then you see where you get.
Okay.
Okay, so this already gives you functor between coverings. Oops, sorry. Between coverings of X to pi 1 X X0 spaces. And the claim is that this functor is an equivalence of categories. Exercise, but of course it's not trivial exercise, it's easy modulo standard theorems from homotopic theory, like the homotopy lifting property, etc. Now this depends on the choice x0 of x0. This you can see it's very much analogous to this Galois correspondence. Yes, so the absolute Galois group of field is very much analogous to pi 1, and coverings are very much analogous to extensions. And in fact, you have the notion of the group of deck transformation of a given covering, and this is analogous to the notion of Galois group of a given extension. And the deck transformation of the universal covering will be exactly the analogous to, or will be exactly the group pi 1. And now I wrote spaces, but here I really want to say sets. So covering X is equivalent to pi 1 sets, and you can take it a bit further. So if you don't want to choose point, so you can do still covering of X. And yes, this is true only when X is connected. Otherwise, you don't feel the other connected components. But now I want to do something which will be true for any X, and I don't want to choose points, so I would write like this, pi 1 of X, pi 1 of X sets. So I have to define two things. What is this guy? So this is a fundamental groupoid, like this is a fundamental group, and this is a fundamental groupoid. I will define it in a moment. And what are sets over a groupoid? So let's start with pi 1 of X. So objects of pi 1 of X, it's just X, which look like huge, yes? Before we have a group, which if you want to make a groupoid out of it, so we have only one object, and here we have some huge thing. And morphisms between X and Y are passes between X and Y up to homotopy. So passes, but two passes considered the same if they can be shifted one to the other. Now it looks like huge, but you see that if X is connected, so basically all the objects are isomorphic. And so if X is connected, then this fundamental groupoid is just equivalent to B pi 1, to the B of the fundamental group. So nothing happened. And but it does not depend on the choice of the point. It's more natural object. And if we have a groupoid gamma, so another definition. So if gamma is groupoid, then gamma set is a functor from gamma to sets. So it's a bit misleading notion, yes, because it's not actually one set, it's functor from the groupoid to sets. So you see that if gamma is Bg for some G, then gamma set is just G set. So you see how this statement generalizes this statement. So if X is connected, then this statement just becomes this statement. And if X is not connected, then of course also it's more or less the same, because if X is not connected, under reasonable assumptions on X is just disconnected union of several spaces, and for each of them it's 2. So basically this is just more fancy way to say this, but it's more fancy and it's nice because you don't really use the choice of point. Okay, and this reminds me that I can give another definition of this pi1. So I said that pi1 is I can consider that the objects will be all points and morphisms are passes. But now I can define it differently, so it's equivalent to another exercise pi1 of x to the category of all universal coverings of x. So again, I usually say the universal covering as if there is only one universal covering, but this is not exactly true. If we choose a point, then there is a canonical way to construct the universal covering, and in general, the universal covering are all isomorphic, but they are not canonically isomorphic, exactly as the algebraic closure. So here I have to be a little bit more careful. So if X is connected, then I know what is the universal covering. If X is not connected, so what do I mean here? I mean just maps, the covering maps from X to X tilde to X. So coverings with X tilde connected and simply connected. So in this case, indeed, there is more than one universal cover. Okay, maybe it's not a good name in this case anymore, but you basically take a connected component and take its universal cover. So if I have not connected space, I mean by universal cover, I mean a universal cover of some connected component.
This exercise is looking like a theorem, right? It's not.
Okay, modulo standard facts in algebraic topology. So first of all, you need some assumptions on X, which I always suppress. So in order all this theory to work, you probably want X to be connected, locally connected and locally simply connected. Yeah, so you don't want Cantor sets, you don't want some bizarre things. You want nice spaces, and this is a theorem which called the existence and uniqueness, in a sense, of the universal covering. So again, what I'm doing here, I'm taking some more classical things that you probably know, and I rewrite them in more fancy way. So the rewriting is an exercise. The actual facts have some meaning inside them. So the things that go inside is this homotopy lifting property, but also for universal covering, there is also this construction of universal covering that demand a little bit more. It demands this locally simply connected, but once you have it, then everything is straightforward. Yeah, so those exercises will make sense for you only if you did some basic course in algebraic topology. The same like the question about Galois theory will make sense for you if you did basic course in Galois theory.
The left-hand side is a group or a groupoid?
It's a groupoid. It's a fundamental groupoid. You can consider the right-hand side as its definition, but then there is no exercise. So if you want to make an actual exercise, I want to use this definition. So you kind of have two definitions of fundamental groupoids, which are equivalent. So the exercise to show that they're equivalent. But I claim that the second one is slightly more powerful than the first one, because the first one says to you that if you want to define the fundamental group, you need to choose a point. And the second one says that if you want to define because once you choose a point, then it's an object in the fundamental groupoid, and you take the group of its automorphisms. The second one, in order to define the fundamental group, you need to choose an object in this guy, meaning choose a universal covering. And then once you choose an universal covering, then you can get this group of automorphisms. And this is less to choose, because you always, so if you have a choice of a point, then you can, yes, okay, maybe the way to say it is that you have a natural functor in these directions. Those two categories are equivalent, and you have a natural functor to one direction, which is fully faithful and essentially surjective, but you don't have a natural functor to the other direction, because you cannot, out of a covering, to choose a point. If you have a point, you can choose universal, you can construct a universal covering. If you have a universal covering, you cannot construct choose a point. And this is kind of indeed more powerful. So for example, if pi1 is commutative, I think you can get more or less automatically here. Okay, basically you have a canonical universal covering in this case. And it's not the case, and you don't have a canonical point. So this gives you this gives you pi1 for lesser price than usual, because you just need to choose a universal covering. And in fact, there is an even lesser price. So there is a notion of Deligne point. So the Deligne, I don't know how to write Deligne point in X is a map phi from Y to X where Y is simply connected. And basically, once you have a Deligne point, many things that you usually need a point for them, you can define using the Deligne point, using a Deligne point. For example, the group pi1, because you can choose any point that you want in Y and consider its image in X, and then ask what will be the pi1 of the image. And you get some group which you associate to Y and to a point that you choose in Y, so it doesn't look canonical. But now when you choose two different points in Y, simply connected, of course, simply connected and connected. Then I claim that you got the same group, and not just isomorphic group, but canonically isomorphic group, because when you choose 2 points in Y, you can connect them with a path and get isomorphism between those two groups. But if you choose a different path, you get the same isomorphism, because any two paths are homotopic. So choosing such an object, a Deligne point, in many cases can replace you a choice of a point. And this is kind of joint generalization of a point and universal covering. Universal covering is a Deligne point, and the point is a Deligne point. Okay, questions? No questions? So I think we are ready for Unit dilemma. So Unit dilemma is in a sense kind of highlights of category theory, or at least at the beginning. And in a sense, it's kind of a posteriori justification for category theory. So you remember that when I said that if you have some object that you think of it as a point, then all the objects in the world, then you can consider morphisms from point to X, and this will be the underlying set, if you have some natural candidate for a point. But even if not, you can consider if you have just an object S, so you can consider this, and you can call it S point of X, which in a sense is the underlying set of X from the point of view of S. And now the nice thing is that if we range over all S in our category, then we basically get all the information on X. So definition or notation, I don't know. if we have category C, let C be a category. So first of all, we have the notion of pre-sheaf on C. Pre-sheaf of sets, which is just, it's maybe kind of a stupid name, it's just a functor from C op to sets. A contravariant functor to set. Now we have the unit embedding, it's a functor from C to pre-C.
Didn't define the functor.
Well, I will define it in a moment. I'm defining it now. And I of C, I want to get an object in press C. Oh, sorry, funct. Yeah, so press shifts are just functors between C op and set. So objects in press C, it's a functor. So I have X, I want to get a set now. It should be contravariant. Sorry. So I want to get a set. How do I do it? Just more. Nope, not C. And here I have Y. More between Y to X. Or maybe let's call it S. And you remember that this was just a set of S points. Yeah, so to construct this idea of taking S points, when we take it all together for all S, we actually get one functor, one contravariant functor. Oh, no, I don't want to do it like this, I think. No, I don't want to do it like this. I want to do it like this. Yes, so I'm taking X and replace it with a functor of S points. So it's functor to sets from all the objects in C. And here is a unit dilemma, theorem. Theorem, unit dilemma, or actually an exercise. I is fully faithful functor. I is fully faithful. It's not essentially surjective, but it's fully faithful. So what does it mean? It means that if we consider the essential image of I, so essential image of I is just all the functors which are isomorphic to element in the image of I. Then we get an isomorphism, and so an equivalence of categories. So I gives an equivalence of categories like this. But now it is essentially surjective because we took the essential image. So instead of constructing objects, we can construct functors, pre-sheaves on objects, functors to sets. So in order to make it work, we need to actually choose an inverse, and it's sometimes a problem, but we know that we have such an inverse, and it's unique up to an isomorphism, so there are no too much options. So how we can use it? So instead of constructing an object, we can construct a functor. And then one has to prove that this functor is representable. But okay, so maybe I should say definition. A representable functor is element in image I. So it's functor that's isomorphic to a functor that can be obtained for an object. So it's represented by this object, so it is representable.
So is it a functor?
What?
Okay, and this is indeed a functor, right?
It is indeed a functor, a contravariant functor to sets.
Okay.
Yeah, so why for me it is a justification of category theory? Because category theory So what we say in category theory, we say let's forget all the internal structure of objects and consider only morphisms. And you can say why. Yes, so there are more things. Like when you do groups, these groups have, I don't know, have a magnitude. This is an interesting question. What is the magnitude of U group? Why we just throw it away and say, no, let's consider group theory just as a category and we don't lose anything. So first of all, sometimes you lose something. Yeah, I'm not sure in this case of magnitude we can reconstruct it or not. Of course, we can reconstruct it if we have the forgetful functor to sets, but anyhow, we sometimes lose something. But maybe one justification to understand that we don't lose too much is that we can, if we know morphism between any object, all the morphism between any object to other object, like in a factorial way, then we can reconstruct the isomorphism class of the object. So it's kind of cyclic justification, but yet it's I think it's nice to know. Another comment here that unit lemma is very simple, but it has a corollary, which is obvious corollary, but by itself it's not obvious if you don't know unit lemma. So it's kind of funny. So fully faithful functors are one-to-one on objects. So if you have two objects which are maps to isomorphic objects, then they are isomorphic. So the corollary is that if I of x is isomorphic to I of y, then x is isomorphic to y. So this is just immediate corollary of unit lemma, and unit lemma itself is very simple. But by itself, it's not immediate. So I once tried to just prove these things directly, without passing through the proof unit lemma, and it just didn't work. Just the shortest way to prove it is to think about unit lemma, and it's not like evident from the formulation, because so fully faithful means that that it doesn't glue morphisms and you can get any morphism. And here you just have two objects, x and y, and you want to build a morphism between them. So okay, you start with morphism here, then you have to prove that you can build it, but then why if you start with isomorphism, why it will give you isomorphism? And yes, the reason is
I mean, it's
faithful
pretty simple to do it directly
without passing through,
without
without actually proving your lemma.
without actually proving it. I mean, then it's all tautological, so you can say that it's the same, but you can do it.
I just try to do it for CW spaces. You have two CW spaces, and you know
No, I
this,
mean,
but in the homotopic category,
these
like
are
write
just
a theorem. Yes.
the general category.
Yeah, I don't know. Okay, maybe it's not that hard, but
Right, you have hom x6 is the same as hom xy, or hom yx, depending on your side, and then you have a map, and then you have also the other one, and you check the decomposition, and it works.
but you need to check the. I don't know. I somehow felt that it is longer than just to say poof in the lemma and then use it for that. Never mind. Maybe I'm wrong. But yeah, anyhow, it is nice corollary. For example, if you have topological spaces, so there are lots of topological spaces. So let's consider some nice subcategory of topological spaces, CW spaces, but it can be any subcategory that you like. So full subcategory of topological spaces which are nice. And you have two guys here, x and y, and you want to show that they are homeomorphic. But I was interested not in homomorphic, but homotopy equivalence. So it's just a different category and different notion of isomorphism. So, and suppose you know that for any z, more you have the map between more from z to x and more from z to y. Suppose you know that this is a bijection. Then you can deduce that x to y is a homeomorphism, or if you're talking in the homotopic category, So let's do more with the homotopic category. Then you can deduce then that x to y is homotopy equivalence. So for any, if you know for any z, it's this nice subcategory, for example, CW spaces. And okay, this is nice because okay, specifically for CW spaces, in order to check this for any z, which is CW space, it's enough to check it for z, which is a sphere. And then you get nice facts.
What did you say? I didn't understand the relation. What is your claim?
I just gave an application of the unit dilemma, but in order to understand it fully, you need to know some background in homotopy theory. Otherwise, you can kind of understand it modulo some homotopy theory. So in homotopy theory, we're interested in topological spaces, but usually not in all topological spaces, but in some nice subcategory of topological spaces. And there are different candidates for different nice subcategories, but I think the most common one is CW spaces. CW spaces are topological spaces basically glued from disks one to the other. And there is a nice, so there is a nice, oh yeah, so okay, sorry. So we're interested in those spaces, and usually we're not interested just in topological spaces and continuous map between them. So we're not caring about things up to homeomorphism, but up to homotopic equivalence. So okay, I assume you know. Oh, it's more relevant to those of you who knows what is homotopic equivalence. But if you don't know, it's an isomorphism in some other category where morphisms define some in different way. And now we want to show that two CW complexes are homotopically equivalent. So suppose you already have a map between them. You have some map between x and y. So it induces a map like this. So you can take all continuous map from z to x and get continuous map from z to y. And it also works in the homotopy category, yes. And suppose that this map is bijection for any z, but not for any topological space z, but any z in this nice category, CW complex. Then the claim is that this original map was homotopy equivalence. And this just immediate corollary of unit dilemma. And okay, the next step of the application to actually apply it, there is some other part here, which is basically the main step of Whitehead theorem, that says that if you want to check this, you don't need to check it for any CW complex Z. It's enough to check it for the case when Z is a sphere. This is some input that you need to know from algebraic topology, but it kind of makes sense because these CW complexes are glued from disks. So if you know it for spheres, then you can expect that it will work.
But
And
you mean locally, in the idea down to earth, you mean locally.
It's not
because
really locally. It's glued for many disks.
No, but I mean I'm low. I mean you need to check that only for disks. This is saying you need to check
It's
only
kind
locally.
of local things.
Because locally it's
not manifolds. Yes, not locally look like a disk. They're glued from disk. It's some different version of locally, not what you usually called locally.
Okay.
A CW complex can be ugly. It can look like this. It just cannot be Cantor set. It can be ugly, but not extremely ugly. And so you get that if this map induces bijection on, in the case that S is a sphere, and the case S is a sphere, this is not just a set, it's a very interesting object, which is called the homotopy group, the nth homotopy group of X. So if you have a continuous map that induces isomorphism of all homotopy groups, then it also induces isomorphism on, then it's actually a homotopy equivalence. If X and Y are CW complexes, otherwise it's not true. Why is it not true? Okay, so I think it's a good time for a break. Do you have any questions?
You mean to the end of the class, right?
What?
You mean to the end of the class when you say a break?
Yes, yes.
Okay.
Break for 1 week, yes. No questions? Okay, guide, do you want to stay to discuss next time? Okay, so see you all.
Rami, can you stay for a few minutes? Or
Yes,
you
but I
already-
offered Guy to discuss
Okay.
with him something
Okay.
next time. But I can
Okay, so
stay. I can stay with you for a few minutes, and then I will call Guy. It's okay.
Okay.
So anyhow, I will stop the recording.